Let me start by thanking the organizers for their hospitality. Is it not working? Is it working this way? Yes. Okay, then just put it a bit higher, maybe here. Yeah. Is this audible like this? Very good. Okay, so I thank the organizers for being so kind to invite me in this wonderful place, in this wonderful workshop. And also allowing me to change the title. I had a slightly more ambitious title which had cuprates and titanates in it, but I realized that that wouldn't fit in a 20-minute talk. So I'll talk about titanates. And the outline of the talk is I'll start with properties of the undoped strontium titanate, which is very short. Then I'll talk about the doped strontium titanate, both the normal and the superconducting state properties. Then I'll have an intermezzo about energy scales and length scales. And finally, a few words on the conundrum of the pairing mechanism, which is not fully understood in this material. So first of all, the properties of undoped strontium titanate. Strontium titanate in its pristine form, if you use oxygens, just use normal oxygen, oxygen 16, is an insulator. It has a gap of 3 electron volts. It is, has a high electrical polarizability. The dielectric constant is about 2000, so that's a lot. And so it's easily polarizable. And actually in 1979 already it was proposed by the now late Karl Alex Müller that this material was a quantum paraelectric below 4 Kelvin, meaning that it's a system that without quantum fluctuations would decide to go ferroelectric, but for reasons somewhat similar that helium doesn't become solid at ambient pressure, it actually doesn't become ferroelectric at low temperatures. However, it's relatively simple in this case because it is close to becoming ferroelectric to push it in that direction. One direction that was actually initiated by Müller was using a calcium substitution on the strontium side, or as was found out later by Ito in 1999, you can do oxygen 18 substitution on the oxygen 16 positions, and because the oxygen 18 is heavier than oxygen 16, you suppress the quantum fluctuations a bit, but just enough actually to push it across the boundary of becoming a ferroelectric substance at low temperatures. There's ferroelectric transition temperatures, Curie temperatures, that depend on the doping, but it can get as high as 30 or 40 Kelvin. I'll show you, actually there are examples here. Then at some point, the group in Cambridge, Rowley et al., realized that, or said, okay, this is interesting because it means you have a quantum critical point as a function of the oxygen 18 substitution. At around 30% substitution, you go through a transition from paraelectric to ferroelectric, and so this is a quantum critical point, and maybe this quantum critical point may also be used to make the system superconducting. I'll tell a lot more about that, also about the superconducting phase later in the talk. So what's shown here is that effect. This is a very recent paper where we studied that in my group, where you see the dielectric constant as a function of temperature for just the oxygen 16 strontium titanate. So the dielectric constant is 2000 here, and then it started to drop a bit. If you go to 50 Kelvin, it's maybe 300 or so. Or 500, and then if you put in oxygen 18, so at around 30% doping, this thing explodes. It goes in principle to infinity, and then if you go even to higher, it is ferroelectric, and now if you warm it up, you go through a normal thermodynamical phase transition at finite temperature, where it goes from ferroelectric at this side to paraelectric at that side. So this you can tune, and this is a diagram, temperature versus oxygen 18 content diagram, where you see that precisely oxygen 16 here, temperature goes to 30 Kelvin there, it's just paraelectric all the way. And now you put in oxygen 18, at some point you hit this quantum transition, and now it starts to become ferroelectric over here. And so at close to 100% doping, you have to go to 25 Kelvin, and that's your Curie temperature. in the oxygen 18 strontium titanate. There's a lot more to say about it, but I'll not go into all these details. Now, now about the material. If you think about doping it, well, before doping it, it's already good to know what the electrons would be doped in. It's not possible to put holes in this material, but you can put in electrons. So these electrons go into bands which are 3 electron volt above the occupied oxygen type of bands. And so this is on a very expanded scale along different directions, these 2 panels. And so the splittings that you see here are caused, the big one is caused by spin-orbit splitting on the titanium 3D shell. And then the small splitting has to do with a small distortion in the material. If you go below 100 Kelvin, it's no longer cubic, it becomes slightly tetragonal, and that causes the splitting over here. So if you now dope electrons in there, you can calculate from this band structure what happens. So you start by filling this first band. At some point you go through, let's say, Lipschitz transition, where you start to occupy a second band at a critical doping. That's calculated over here, 7 times 10 to the 7 per centimeter cube. And then at a second critical doping over here, you start to occupy the third band. And so most of the game that we are talking about is in doping ranges where you go maybe as far as this and down to almost zero doping. That's what we were talking about. This is what the Fermi surfaces look like. It looks like they're sort of, strange-looking sea animals with legs in 6 directions. That's the outermost Fermi surface, the blue one, the blue bands over here. The orange bands over here. And then inside there are 2 spheres essentially, and that's the red band and the blue band. And so if you can of course try to measure this thing. There have been all the attempts, but these are much more recent data from the group of Cameron Benia, where they measure the quantum oscillations for different dopings. So the lowest here is 5 times 10 to the 17. So you are somewhere just below that red curve over here, and then you go to higher and higher doping. And so you start to see different patterns. Of course, I'm not going to explain these data, and I hope that you don't press me on that, because this is really Cameron's business. But okay, there we are.
No, I'm just going to ask a simple question. Just for my own information, so the band splitting, is that purely from the octahedral tilting transition? It's not from some...
This one is from the octahedral tilting, and this is spin-orbit coupling on the titanium 3D.
So the spin-orbit gap is bigger than the...
Yeah, it's about 30 milli eV. That's the Wien code prediction. Wien code is not entirely accurate, so this is where the predicted let's say critical point would be as a function of doping. Experimentally, you find it about 2 times higher actually. There's a log scale, and also this first band you reach a bit earlier than was calculated in the down. So you should imagine that in reality this band is a bit higher and that one is a little bit lower. But the general structure is there, and so for at least qualitative purpose of qualitative discussions, this band is what we will keep using. What was also plotted in the same paper from the Cameron Benia group was as a function of doping for what I just showed, these band fillings. You also see TC. And so they use 2 types of samples, the ones that are doped by putting niobium on the titanium side, and other ones where you make vacancies in the oxygen lattice. Both have the effect of doping electrons in the system. You can measure how many electrons by doing Hall effect, or actually by using these quantum oscillations. And you find that there's a first dome and a second dome. Now you shouldn't forget, this is a dome on a log scale. So if you put it on a non-log scale, it looks very different from a dome actually, or it's a sort of distorted dome. But this looks like a double dome, and the speculation is that these domes probably have to do with the fact that you are filling different bands here, and that gives a bit more structure than just a single dome. That's the idea. Another important property here is the number of carriers and what the mass is of the carriers. And there are different ways of measuring the mass. I'll show you the specific heat in a second. This is another way where we use the optical conductivity to get these signals. It's very difficult for these materials, I can assure you. We had to make very thin plates and do transmission and also reflection, and so a combination of things that allowed to determine these optical conductivity curves. And what you see here is the Drude peak at low frequency. in this red curve, and then there is the phonon. I'll say a lot more about this phonon because that's the soft ferroelectric fluctuation of your system that is very sensitive to everything. It's sensitive to temperature, it is sensitive to what you dope your material with, and so if you put in dopants, then actually it shifts up in frequency, and moving up in temperature also makes it shift up. But the important thing here is actually this peak, the Drude peak. So if you know the Drude peak and you extrapolate it, the tail, you can integrate the spectral weight in this Drude peak. It's done over here. This is the integrated spectral weight in there as a function of frequency. It sort of saturates, but then of course you hit also this phonon, as I already said, and you get other things up there. But if you just extrapolate it as it would be for a Lorentzian line shape, then this area corresponds, the spectral weight corresponds to something that's proportional to the doping, this x over the unit cell volume times the electron charge square, divided by the mass, the effective mass of the particles that form this Drude peak. And so this is for different dopings here. For two dopings, I'm going to use that information in the following plot. And so, but before I show that, I first show the specific heat. That's another way to do it. If you make a plot of C over T versus T squared, then the intercept extrapolated to zero temperature gives you something that's proportional to the density of states at the Fermi energy, and the density of states has a very simple relation to an effective mass. So what we actually did is say, okay, we take the density of states as it is measured with this technique. We take the density of states as you calculated, as we actually did calculate from the LDA calculation, and that ratio tells us what the mass enhancement is. And we can do exactly the same thing also, as already explained, for the plasma frequency or for the free carrier spectral weight. And so that gives you two different estimates of the mass enhancement, one coming from specific heat, the 2 points that I just showed you, other points from the literature also, and then there's a number of points that actually use this, which ones are those? It's probably the two red points I forget, that actually come from the optics. So the optics and the specific heat give basically the same information. Your effective mass is twice as big as you would calculate from this bean code calculation for the band structure that you just showed. Okay, so I'll say a bit more about this mass enhancement, but there's another piece of information you also get from the Drude peak. The width is proportional to the quasiparticle lifetime in a simple quasiparticle picture, if you have quasiparticles. And so we can just take that width and plot that as a function of temperature that is shown over here for 4 different dopings. And so the dots are just the width, the way it is measured from the optical data. And the lines are a fit, assuming that you have T squared plus some background, plus some residual scattering. And so this is T squared. That fits very well for all cases except for the highest doping, where you see there's a bit of a deviation. You would actually need to put in a T cube additional term to get a better fit. This T square was further analyzed in another paper by the Venia group. Here it was displayed as a function of T squared. They have many more panels. I just show this one here. But in all cases, if you plot it this way, you find straight lines. And so these straight lines also tell you that you have this form for 1 over tau. It's a constant, residual value, plus something proportional to T squared. And that's true up to around 100 Kelvin. Beyond that, you actually go into a different crystallographic phase, and there's no longer this behavior also. Now, at the time when we had these data, we speculated maybe some kind of Fermi-liquid behavior, but it couldn't be, it could be for the higher dopings, but it could not be for the lowest dopings because there is no umklapp anymore if the Fermi surface gets very small. Even for a very small Fermi surface, if you have 2 bands, you can have another somewhat related thing called Baber scattering. There's always an umklapp. And, but also that vanishes if you only occupy a single band. So actually there is no way that you could actually find T square in the scattering rate of the electrons in the electrical transport. There should be no scattering of that kind. You would get into higher order terms, so that would be T to the power 4 kind of thing, first of all. But it's really T squared. So a possible solution that was proposed by our chairman of this session and his collaborators, that you actually have 2 phonon scattering processes. They solved these diagrams. It's a subset of these diagrams that went to this formula over here, but indeed the dominating term is T square, and that has to do with just the electrons shaking off two phonons at the same time. Oh, that time, I mean, there are relativistic effects at play here. And so if you do that, you, so there's another thing you can also wonder, okay, where does this factor of 2 in the mass come from? That is important for the story about energy scales. And that actually has to do with electron-phonon coupling. So the electrons couple to the longitudinal phonons. Those phonons have energies of more than 25 milli-electron volts. They do not couple to the transverse optical phonons, or very, very weakly at least. But if you just assume these couplings here that you can actually calculate from the data also, you get a pretty good fit to the entire spectrum, including a mid-infrared band that I didn't mention before and won't mention anymore. Also, it gives you a pretty good fit with ARPAS. This is an ARPAS paper. And okay, so it gives you the following energy scales. The gap, the superconducting gap, is smaller than 0.3 milli-electron volt if you believe BCS. The Fermi energy is 2 milli-electron volt at least, or more, up to 100 milli-electron volt, depending on the doping you have. The ferroelectric fluctuation is, the TO mode is 2 milli-electron volt, but that one doesn't couple to your electrons, and the corresponding LO mode is, the longitudinal mode, is at 22 milli-electron volt, so that's way above the Fermi energy. And so for the lowest dopings you have really this hierarchy, that the smallest thing is the gap, that's the electron, the range around the Fermi surface that is used for making a superconductor. Then you have the Fermi energy, which is at least 1 order of magnitude bigger than this value here, and then you get to the first phonons that you couple to, and that's yet another order of magnitude bigger. So especially for this part, you are in a strange regime, which is called of the anti-adiabatic regime, where the usual treatment, Migdal-Eli-Asberg, wouldn't work. That also has some peculiar consequences for energy scales, or the energy scales are peculiar. If you calculate the Bohr radius, the effective Bohr radius, that is huge in this case of strontium titanate. It's about 300 nanometers. And that has a consequence that the Thomas Fermi screening length is 100 nanometer if the Fermi wavelength is 37 nanometer, meaning that you are in sort of opposite regime as you might think. If it's very dilute, like in cesium, this ratio lambda Thomas Fermi over lambda f, I mean 1 over lambda f cubed is something like the density, and this is scaled by the Thomas Fermi length. This is 0.05, so that is actually quite dilute from that perspective. In strontium titanate is 20, so it's a high density superconductor. I'm also saying that to tease Kamran Benia a little bit, because he has rightfully also said the opposite. But it depends on what you compare your density to, and if you compare it to the Thomas Fermi screening length, it's small. So it's big. Now, why is that relevant? Well, it could be relevant because if you calculate what the screened interaction between electrons look like, this is what it looks like in cesium for these low density systems. But for high density systems that you effectively have, you don't see these oscillations anymore. Or if they appear, it's at some very high value of kf times r, which is really getting irrelevant. So this is really in the regime of more like normal Thomas Fermi screening without any of these oscillations or very weak ones. And here you have those oscillations. Another thing that's important is that the entire scale over here is scaled by factor 1 over epsilon b, where epsilon is your background dielectric constant, which was 10,000. And so there is actually no Coulomb interaction. Now, meaning that the Coulomb interaction couldn't possibly play any role at all as electron-electron scattering. So that wouldn't give you a T square. It would also not play a role in any kind of pairing mechanism because it's just essentially completely negligible and repulsive everywhere. Now, there have been other proposals for pairing, and that was, this came from Edge, Kadem, Aschauer, Spalding, and Balatsky. They said, okay, let's assume that you do couple to these soft ferroelectric modes, and if you make that assumption, you find that you can reproduce this dome over here as a function of doping, and if you now would make your system ferroelectric gradually, or more ferroelectric, you would see this Tc go up. So by moving it closer, let's say, to the quantum critical point where it becomes ferroelectric, Tc would go up, and also the dome would shift a little bit to the left. So several people have done it. We started with only 3 samples. Then there was a group in Japan who did it with 4 more samples. There was another approach using calcium instead of strontium from the Cameron-Bania group. And in the end, again, Rischau in my group made about 90 samples with different oxygen 18 concentrations and dopings. And that gave this plot here. All these papers confirm that indeed, if you go to higher oxygen 18 content, Tc goes up quite a lot, and the dome shifts to the left. You can see it somewhat better over here in this graph. Oops. This is the oxygen 18 concentration. This is the doping, and so there's a slight shift to the left, and in particular, there's an increase of Tc. Now, this is a significant result because the increase in Tc is the opposite as to what you expect from BCS theory, and it is 10 times bigger, this effect, at least 10 times bigger than the BCS. So it's a really completely different physics. So it was sort of correctly predicted, but there was a problem with that. Namely, as I already said, those phonons that you're coupling to here, especially near the zone center, those are transverse optical phonons, and those phonons don't couple to your electrons, as was pointed out by Ruhmann and Lee. So actually, it was the right prediction in the effect that was confirmed by three different groups. But there's something not quite right about the assumption of why that these phonons couple to electrons in the first place. How am I doing this time? Very good. Yeah, so I'm gonna, in total, yeah. So I just need 2 minutes to wrap this up. So one thing that was not in the paper of Balaski, but that actually may save the day for them, is to say, okay, so maybe if you can't exchange one phonon, you can still exchange 2 phonons together. And since there is some sort of selection rule that would take you from an even band to an odd band if you emit a transverse optical phonon. But if you emit 2 of them, that doesn't happen. You stay inside the same band. And so the idea of N-Guy from 1974 was that you have also these processes. They could be quite important in strontium titanate, but he didn't know the numbers at the time. And so he predicted that these 2 phonon processes could be the mechanism of pairing in strontium titanate. And now, of course, you can use those soft ferroelectric modes. Well, there's a trick to get that number from optics. There's really no time to explain how that is done, but it is explained in this paper. And we got a reasonable value of lambda 0.25 plus a pretty big error bar on that, 0.25 plus or minus 0.1 probably, but it gives you a TC in the right ballpark. Again, there's a huge error bar. So it could be that this is the right thing. This was also followed up by Kieselov and Feigelman, who made more detailed predictions about superconductivity. So it is a possibility. And since there is really no good other candidate, it's a reasonable candidate. So that brings me to the summary. So undoped strontium titanate has a very strong isotope effect on the ferroelectric TC. It's not there if you don't put in the isotope, the oxygen 18, and it becomes ferroelectric if you do. There's a very strong electron phonon coupling, gives you a mass reionization of a factor 2 for the electron doped strontium titanate. There's a T-squared charge transport scattering below 100 Kelvin that is sort of understood, but there are a few loose ends also in Dimitri's story. I think he told me it's not going to do exactly the right job at very low temperatures, and so Dimitri is waving his hands a bit about that, I think. And so there's a question there, but maybe it is like that. And then there's a very strong isotope effect on the superconducting TC, which has the opposite sign as BCS theory, and it is at least 10 times bigger than BCS theory predicts. So that's confirmed by 3 different experimental groups. It's a real effect, and it was actually predicted, but somehow not an entirely correct model. There's a sort of patch on that model that could be reasonable, where you say, okay, that also has to do with the 2 phonons. So that actually binds together this story and that in maybe an overall picture of the transport that it would mean that the transport in strontium titanate is dominated by 2 phonon scattering processes. Okay, if that is abnormal enough for this workshop, I don't know, but it is pretty abnormal. So, moreover, it's something that could also be relevant, I think, in some of these bilayer graphene materials and some other materials also. Thank you very much for your attention.
Okay, Shankar.
Very nice. I agree. It looks like phonons. So did you or anybody try to correlate, like in all the metals, getting a lambda transport by looking at very high temperature linearity, extracting a lambda transport from that, and correlating with the lambda superconducting 0.25 or whatever it is? They should correlate if they're phonons within 10% level.
Yeah. I don't think that has been done. Of course, this
you understand what I'm saying? All you need is the slope.
Yeah.
Yes.
Extract 1 over tau, equate that to 2 pi lambda t.
Yeah,
that gives you lambda transport.
Yeah. Yeah.
You have an estimate.
Yeah.
They should be within 10% of each other, like they are in every metal.
My answer, because I tried to do that. So
For this material?
I took out a squared model, I extracted the coupling constant, plugged into a simplest formula for TC. It didn't get into the ballpark of 110. It was more like 0.001. But the phonon spectrum is complicated. So if you want to do real calculation, you really have to take into account the dispersion of the mode of the brilliant zone.
Resistivity, you need the measured resistivity where the resistivity is clearly linear, because this t squared phonon is not going to give. So there are some issues
that's a phonon. That's a 2 phonon t squared.
No, I understand that, but still, it should be linear.
It's never linear. It's never
not
linear
anywhere.
No. Anywhere.
That's the problem.
Peter?
Hi, Dirk here. So I had a question about M star. So there are quite a few papers, if you go back 30 years, saying the plasma frequency in this material is temperature dependent. So it changes, I think, a factor of 3 or 4 between room temperature and, say, 20 Kelvin.
Yeah.
Sometimes people attribute that to changing M star. The alternative is you have to attribute to something else changing, like the density. I was just wondering if you had any idea what it could be, and does your M star determined in this way give you a number that changes the temperature?
Yeah, it changes the temperature.
By factors of 3 or 6?
No, a factor of 2 if you go to room. Actually, it's getting smaller if you go to room temperature. It goes down.
Yeah.
Yeah. You may say your polarons are getting lighter or something like that.
Yeah.
That's a hand-waving way to talk, that we talk about it.
But is your understanding of that just, is it polaron physics, or?
I think that if you want to use a label here, then polaron would probably be the closest description of it. And of course, if you...
Because one of your papers actually argues that the polaronic effects aren't strong enough, unless I misread it.
Maybe you misread it, because I think we had quite a series of papers with the phrase saying, okay, these are polarons, but there are large polarons.
Yeah.
But still polarons. At least for the lowest dopings, you definitely are in that regime.
Okay, I think Andrei has a Zoom question.
Yeah, I'm in charge of Zoom questions. I'll be Chandra Varma for the next few seconds. Transverse phonons do not couple to charge density of electrons, but can they not couple to electron currents? Question mark.
Can you repeat the question?
Transverse phonons do not couple to charge density of electrons, but can they not couple to electron currents? Question mark.
I think they always couple to electron currents.
Chandra wants orbital occurrence?
Yeah.
Yes.
Okay.
Rafael?
Hi. Yeah, so I have just one comment and one question. The comment is, there is a coupling allowed via the spin degrees of freedom. And initially, they thought this was going to be small, but there are recent DFT calculations from the Maria Garcia Soto and her collaborators that actually show that this is not a small coupling; it's actually pretty large. So just to put that also as a possible, there are lots of other issues with the mechanism, but I think that it is a possible mechanism. Now,
spin degrees of freedom.
Yes, it couples via K cross sigma.
Oh,
spin orbit.
Yeah.
So since there is spin orbit, I see.
Yeah.
Right here. Yeah.
So, but my question is, so there were also recent work from I forget I know that camera is also in the paper, where they look at these, they found there is a finite Q, very soft phonon that comes from the hybridization of the acoustic and the acoustic transverse and the optical transverse mode. There is a hybridization, they get very soft. And I think Pierre Little would even estimate and said that maybe the system is closer to the finite Q instability than to the ferroelectric. So just to see if you have any thoughts about this idea and how it plays out with the phenomenology of this compound.
Yeah, I actually only recently became aware of it. It turns out to be something that I found it in a paper that Tossati, Eriok Tossati, wrote for the special issue in Physica C of that we are in the process of creating right now, in memoriam of Carl Alex Müller. It's stuff that he discussed with Carl Alex Müller 40, 50 years ago, never published, and now he has actually written about it. He didn't speculate, neither have I thought about whether that could play a role in the pairing mechanism, but yeah, since you couple two phonons, yeah, well, maybe, yes.
Kamran?
Well, Dirk, I agree with all you said. I just want to make a comment about, mass at high temperature. So we are on the, and this is actually related also to Shankar's, question. It never becomes T-linear resistivity. So there is no T-linear resistivity here. The way we understand it, and if you put the numbers, the mean free path is ridiculously short. And one way to just, remedy this is to suppose that the mass is increasing with temperature, not decreasing, but increasing. No. This is what comes also from thermopower. Okay. So the mass increases by a factor of 5 or 6, but if we use just, conventional Pisarenko formula of thermopower. And this is what, to my understanding, we don't understand at all. Okay. It should be some polarity effect.
We communicated about it, but frankly, I need to look at my graph to remember, to be sure that what I stated was correctly stated.
Yeah, I think the mass goes up even from plasma
frequency. Mass is also up.
Goes up. Okay.
Okay, yeah. 30 seconds, Rivas, for a question, 30 seconds for an answer.
I have a naive question. So you mentioned the substantial isotope effect. So in an elemental material, it's relatively straightforward, but I mean, this is a ternary compound, and how easy it is to figure out which phonons do what, because there are many of them, and what would be the isotope effect on the phonons that you are interested in?
Well, normally you would just calculate the, what normally happens in BCS theory is the TC is proportional to the phonon frequency, and then e to the power -1 over lambda. It turns out that the phonon frequency does not enter into the lambda. There's a compensation there that makes it independent of it. So it's only the prefactor. So making your material heavier means that the phonon frequency goes down. And so that sets the effect in BCS model. And so that gives you an...
30 seconds for our exchange. You can continue. Thank you, Dirk. And now we're going to cosmology. There is a workshop in parallel, I guess, on black holes and also on momentum relaxation in other cuprates.